This is SpaceTime Series 25, Episode 113. Coming up on SpaceTime, discovery of the nearest black hole to Earth, how galaxies grow from the cosmic web, and China launches 3 more spy satellites. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered what, right now at least, is the nearest black hole to Earth. The newly found monster, which is some 12 times the mass of our Sun, was detected just 1,550 light-years away. The findings, reported in the Astrophysical Journal and on the pre-press physics website archive.org, suggest there could be many more similar black holes like this hiding in plain sight. The study's lead author, Sukanya Chakrabarti from the University of Alabama in Huntsville, says this newly discovered bottomless pit is practically in our backyard. Black holes are exotic celestial objects of infinite density with zero volume. They have so much mass that their gravity is so powerful nothing, not even light, can escape, and so they effectively become invisible. They can therefore only be detected by their influence on the universe around them. Chakrabarti and colleagues discovered the black hole after analysing data from the European Space Agency's Gaia mission of nearly 200,000 binary star systems. The authors searched for systems in which one star seemed to be orbiting an invisible companion. Interesting sources were then followed up with spectrographic measurements from a variety of telescopes, including the Automated Planet Finder in California, Chile's Giant Magellan Telescope, and the Giant Keck Observatory in Hawaii. Chakrabarti says the gravitational pull of the black hole on its visible companion star can be determined by these spectroscopic measurements, which provide a line-of-sight velocity due to a Doppler shift. A Doppler shift is a change in frequency in the wave of light coming from an object as seen by an observer. It's similar to how the pitch of a train horn or an ambulance siren changes as the vehicle approaches, passes, and then disappears off into the distance. By analysing the line-of-sight velocities of the visible star, and in this system that visible star was similar to our Sun, the authors were able to infer how massive the black hole companion was, as well as the period of rotation and the eccentricity of the orbit. The black hole had to be inferred by analysing the motions of the visible companion star because it's not drawing material from the visible companion, so there's no accretion disk around the black hole, which would normally be a telltale giveaway feature if it were feeding. And that's the thing, the majority of black holes in binary star systems are in X-ray binaries. That is, they're emitting bright X-rays due to the material on their accretion disks, which is being crushed and ripped apart at the subatomic level as it's being consumed by the black hole. That material only becomes invisible once it passes the event horizon, a sort of point of no return at the inner edge of the accretion disk, beyond which material falls forever into the black hole singularity. And these interacting systems, as they're called, tend to be on short-period orbits, so the black hole and its companion star are close enough to each other for the black hole to draw material off it. But in this case, the authors were looking for a black hole on a long-period orbit, which turned out to be 185 Earth days. Chakrabarti says that based on her estimates, there could be millions of visible stars that have undetected black hole companions in our galaxy alone. This is SpaceTime. Still to come, how galaxies grow from the cosmic web, and the NASA-SpaceX Crew 4 returns safely to Earth, splashing down in the North Atlantic Ocean. All that and more still to come on SpaceTime. A new study has found that galaxies tend to be oriented so that their spin is aligned to the nearest cosmic web filament. The findings, reported in the Journal of the Monthly Notices of the Royal Astronomical Society, provide new details about how galaxies form and evolve. The large-scale structure of our universe appears to be traced by the distribution of galaxies, galaxy clusters and superclusters into a cosmic web-like structure of filaments linking denser connecting nodes. The new research finds that galaxies with bigger bulges tend to spin perpendicular to the filaments in which they're embedded, while galaxies with smaller bulges tend to spin parallel to these filaments. The study's lead author, Stefania Pessanti from the Australian National University, says it all relates to the mass of the bulge. Galaxies which are mostly disks with low mass bulges tend to have their spin axes parallel to the nearest filament. This is because they're formed mainly from gas falling onto the filament and then rolling up. But these galactic bulges grow when galaxies merge, cannibalizing or crashing into each other as they move along the filament. So, these galactic mergers tend to flip the alignment between the galaxy's spin and the filament from parallel to perpendicular. Pessanti and colleagues say mergers must be more likely as galaxies move along the filaments towards each other, and the direction of these mergers drives the spin flip. The discovery sheds light on the formation of two main components of galaxies and how they relate to the large-scale structure and motions of matter in the cosmic web. Pessanti says the motivation for this study was to try and understand why galaxies spin and how they acquire their angular momentum from the material that forms them. Through this study, astronomers can better understand how mergers play an important role in the formation of galaxies, both the central bulge component and the spin flipping. This in turn points to specific formation channels for how galaxies start to spin and how the spin changes as galaxies evolve. Although this same evolutionary process had previously been suggested in computer simulations, this study is the first time that scientists have been able to use direct observations to confirm that the growth of a galaxy's central bulge can cause it to flip alignments. The discovery was only made possible thanks to the development of integral field spectroscopy. It's a technique in which an optical instrument combines spectroscopic and imaging capabilities to build a three-dimensional image of a galaxy and at the same time resolve its internal motions. This study used a spectroscope called SAMI, which is attached to the 3.9-metre Anglo-Australian telescope at the Siding Spring Observatory in far western New South Wales. Researchers used SAMI to survey some 3,068 galaxies between 2013 and 2020. Pessanti says the SAMI Galactic Survey provided spatially resolved spectroscopy, allowing the authors to map the galaxy with spectra at many points across the galaxy. And this tells astronomers about the internal motions of the stars and gas within a galaxy, allowing them to measure its overall spin.
So basically, the large-scale structure of the universe, we as astronomers, we usually call it as cosmic web, because it looks like a spider web and it's all made by galaxies and gas. So galaxies are not just randomly distributed in the universe, but they have this particular structure. So we can think that since they have such an ordered structure, that the properties of the galaxies are affected by this kind of structure. And what we found is particular that the spin of the galaxies actually interact with the filament in a way that has the center part of the galaxy, that's the bulgy part, grow, then they change the alignment with respect to the filament. So for galaxies with low bulge mass, they will spin in parallel with respect to the filament because they are made from the gas of these filaments and they will conserve exactly the same orientation. While as the galaxy merge and grow, so the bulgy part becomes more massive, then we have a flip of the alignment with respect to the filament from parallel to perpendicular because of the conservation of the angular momentum. And so we were able to detect this signal in the nearby universe, so using galaxies close to us and using observations. And it's a really weak signal to look at because it depends on exactly the cosmic structure, but we were able to trace it using some really deep observations.
And so what happens with the perpendicular galactic bulge after a few billion years? Are they likely to go back to parallel or do they remain perpendicular forever?
So that's a great question. So after the spin went perpendicular, if there is another accretion of gas, the spin can actually flip back to parallel. However, and that's research project that we are actually looking now, we need to take into account the impact of the black hole activity, because the supermassive black holes within the galaxies, they actually prevent further gas accretion, so they actually help to keep the spin of the galaxies perpendicular, and so they will prevent any kind of gas accretion and reparallelization of the spin. Since we achieve these results with respect to the mass of the bulge, then the next question that we ask ourselves and we are looking into now is, what is the role of the black hole activity into this?
Now, you said you looked at some nearby galaxies as well as more distant ones. When you looked at those nearby galaxies, are we seeing that same trend there? I mean, the angle of tilt of our Milky Way galaxy, is that the same as Andromeda or the large and small Magellanic Clouds?
So we look at nearby galaxy, but not this close. So not Milky Way, not Andromeda, not the Magellanic Clouds, because it's really hard to trace the cosmic web for such close objects. So we look like still galaxies that are close to us, but not that close. But what we think is that the signal, this kind of trend, actually evolved with time. So galaxies that were much farther away from us, they will tend to have a parallel trend, because events such mergers becomes more likely with the proceeding of time up to now. So galaxies that have close to us will show more perpendicular trends, a stronger signal for the perpendicular trends, while galaxies that are much farther away, they will have a more parallel trend. So now we are also doing observations much farther away. So for galaxies that are at around 3-4 gigayears, look back time to understand if this signal evolves with time. So we are doing exactly the same observation we did for the nearby universe that's much farther away to understand the evolution of the signal with time and prove this theory.
Have you been studying spins within galaxies as well, or just the overall bulk of the galaxy?
So we actually have been studying the spin that the galaxy has from stars, so from the stellar component, as well as the spin from the ionized gas. So with our observations, we can actually distinguish between the two, so the ones that are given by stars and the ones that are given by gas. And we look also if there is any kind of misalignment between stars and gas, and if they will behave in the same way with respect to the filaments. And for the study that we are doing to understand the impact of black holes in these spin filament alignments, we are actually digging more into these separate stellar and gas spins within the galaxies.
When the Event Horizon Telescope first imaged the black hole at the center of the Milky Way, Sagittarius A star, the spin of the black hole along the accretion disk is different to the spin of the galaxy as a whole.
Yeah. So we can have misalignment within the same galaxies for different components, even like the bulge and the disk within the same galaxy. So two different structural components of the galaxy, but actually the kinematic can be different. They can spin in different ways. And that depends on how the bulge or the disk have been formed, from which material they've been accreted or merged. So both the gas and stars keep their remember from the material they've been formed, and they spin in order to maintain the equilibrium for the whole galaxy.
So this is telling us a lot about the evolution of individual galaxies.
Yes, definitely, yes. And also looking at for example, separate alignment of bulges and disks, we can see how the spin of these components is aligned with respect to the filaments, and we can understand the formation pathways that lead to that specific component. So it's actually a powerful tool to understand galaxy evolution and galaxy formation.
So we're going to see a lot of change in the views we're getting here within the Milky Way as Sagittarius dwarf plows through the galactic disk again and again over the next few billion years. That'll change our orientation completely.
Yes, definitely. Yeah. And also something, so in order to better understand this, what astronomers do is to look at galaxies outside the Milky Way that is similar to the Milky Way. So they are called Milky Way analogs.
Yeah.
So galaxies that have the same properties of the Milky Way so that we can study them within their environment and we can trace the, for example, cosmic web structure. And so we can have a better understanding on how our galaxy has been formed and is going to evolve as well.
That's Stefania Basanti, an astronomer with the Australian National University. And this is SpaceTime. Still to come, NASA's SpaceX Crew 4 returns safely to Earth. China launches another 3 spy satellites as it continues its preparations for war. And later in the science report, researchers confirm there's been a decline in global life expectancy because of COVID-19. All that and more still to come on SpaceTime. NASA's SpaceX Crew 4 have returned safely to Earth, splashing down in the North Atlantic Ocean off the coast of Florida. The team had just spent 6 months aboard the International Space Station. The crew had launched from the Kennedy Space Center aboard a Falcon 9 rocket back on April the 27th. The return of the SpaceX Dragon capsule Freedom had been delayed by a day due to wet and windy weather conditions in the recovery zone off Jacksonville. The descent took about 5 hours, with the spacecraft splashing down into choppy seas and quickly rendezvoused by the SpaceX recovery vessel Megan.
Freedom, SpaceX, we see nominal trunk jettison.
So great news there. The trunk has been jettisoned and it looks like everything performed as expected during that trunk separation. So with the telemetry, looking good, the nitrox system is now primed for cabin and suit cooling, and the heat shield is now exposed and ready for that atmospheric reentry.
SpaceX Freedom, mid-copy your trunk separation.
Copy, Freedom. We had a handover there, but just to confirm, we did see a nominal trunk jettison.
Freedom copies.
Some good comms between the crew and the core here in Mission Control. Now up next, we have the final steps that Dragon will perform prior to reentry, the slew or maneuver to deorbit burn attitude and the deorbit burn itself. Now this is the last time that the forward Dracos, which are the 4 thrusters located on top of the vehicle, will ignite. The deorbit burn will place Dragon on a precise trajectory to return to the splashdown zone off the coast of Florida and will last about 17 minutes once it starts.
We are now in the burn attitude, as you mentioned. The Dragon slewed or positioned itself to get into that burn attitude. And once this deorbit burn is complete, the next milestone that we can look ahead towards is the nose cone closing. The nose cone has been opened since the crew docked to the International Space Station on April 27th, but it will close up for the reentry process as it protects a lot of the vital equipment that is necessary. So that nose cone will close after this deorbit burn, but it needs to be open right now so that the thrusters are exposed to be able to have the burn occur. And we do have confirmation that the deorbit burn has begun. This burn is expected to last about 17 minutes. And for these operations, NASA and SpaceX do closely coordinate with the United States Coast Guard to establish a safety zone to ensure public safety, and of course for the safety of those involved in the recovery operations as well as the crew on board the returning spacecraft. Multiple notices are issued to the mariners in advance and during recovery operations, and Coast Guard patrol boats are deployed to discourage boaters from entering the splashdown zones.
Dragon Freedom has not yet entered Earth's atmosphere. This deorbit burn is what will line the vehicle up and put it on its final trajectory to the landing site off the coast of Jacksonville, Florida. Right now, Chell, Bob, Jessica, and Samantha are using their screens to keep tabs on the burn duration. Draco thruster firings and trajectory details like entry angle, capsule perigee, and how much distance remaining until the deorbit burn termination. Dragon is flying itself. Again, it's autonomous, so all the crew has to do is stay strapped in their seats and keep tabs on things. They'll be heading to one of 7 targeted sites supported by SpaceX and NASA. All of these sites are located off the coast of Florida, either in the Gulf of Mexico or the Atlantic Ocean. Spreading the supported sites across multiple locations helps to maximize the return opportunities opportunities for this mission and future crews, lowering the chance that we'll have to wave off due to bad weather.
And earlier today, NASA and SpaceX jointly selected prime and alternate splashdown locations off the coast of Jacksonville, which is our prime today and where the boat is currently staged, and the alternate is Tallahassee, Florida. The selection process works with a lot of different variables, including the space station's orbital trajectory, what landing sites are available and have favorable weather, how much free flight capability Dragon has for the trip home, and the sleep schedule for the returning crew members.
The time from undock to landing at the primary site can vary from less than 6 hours to more than 39 hours. Getting home the quickest comes with some obvious benefits, but we always have to make sure that the crew is properly rested for dynamic operations, preventing us from scheduling 20-plus hour days for them. Trajectory and ballistics experts provide the daily opportunities that would line up Dragon with 7 landing zones and split them into what we call ascending and descending opportunities.
Dragon uses its Draco thrusters after leaving station to execute a series of altitude-lowering maneuvers and to line up with the selected primary site. It can also change to different alternate sites while in free flight if sudden weather moves in that we'll need to avoid. And weather is something that we're constantly looking at, making the final call to proceed about 2.5 hours before the crew undocks. So for the Crew 4 return, we looked at a number of weather items. Some of the obvious ones are no rain or chance of lightning in the recovery zone, both for the safety of the crew inside the capsule and the recovery teams on the water. We're also looking for wind speeds less than 15 feet per second or about 10 miles per hour and relatively calm seas so we can safely execute recovery operations, which includes landing a helicopter on the recovery ship to fly Chell, Bob, Jessica, and Samantha back to Florida. Once Dragon began flying free, we had a number of additional checkpoints to either proceed towards the primary site, head to the alternate, or select a new zone based on real-time weather data. These checks happened all the way up until we're in the final hours before the Deorbit Burn, which is the last burn in the trip home and commits the Dragon capsule to re-entering the atmosphere. And as we've mentioned, this burn is underway. We are hearing good calls that the burn is proceeding nominally or as expected, which is great news.
Development of Dragon for Crew started with Cargo Dragon. Dragon was designed from the beginning for flying humans to space, so much so that even the first Cargo Dragon had a window on it. And before we could fly humans, our teams implemented a number of design upgrades to make sure that both Dragon and Falcon 9 are suitable for flying people, and then put both vehicles through thousands of tests to prove their safety. Now, Dragon is capable of carrying up to 7 passengers to and from Earth orbit and beyond. It is the only spacecraft currently flying that is capable of returning significant amounts of cargo to Earth and is the first private spacecraft to take humans to the International Space Station. Dragon is fully autonomous, which means that it can basically fly itself, but also features full manual override capabilities in case of emergency. Now, standing at almost 27 feet tall from the bottom of the trunk to the top of the nose cone, Dragon is composed of 2 main elements. That's the capsule, which is designed to hold crew and pressurized cargo, and an unpressurized section known as the trunk. And for today, we have already jettisoned the trunk, which reveals the heat shield on Dragon as it prepares to return back home to Earth.
The next step after the Deorbit Burn will be the nose cone closing. It's very important to close that nose cone because it protects the docking mechanism and some guidance and navigation and control equipment. The crew will then begin to re-enter the Earth's atmosphere. There will be a blackout period where we will not be able to communicate back and forth with them. That does last just a few minutes, and that is completely expected. That is happening because the plasma is building up around the vehicle, but the heat shield will do its job and protect the crew throughout that process. And then once the crew has gotten to the other side of the atmosphere, we should have communications back with them, and then we will see the drogue parachutes deploy, then the main parachutes, and then we'll see splashdown just a short time after that. The drogue parachutes slow the Dragon down from 350 miles per hour, so that's still going pretty quick. But then once the main parachutes deploy, it will slow down quite a bit more to less than 20 miles per hour. So after those parachutes are deployed, we will see them be cut. There's a fast boat that goes out there. The purpose of the fast boat is to cut those parachutes, and that's really just to make sure that they don't get caught in the wind or pulling the crew around. So those parachutes will be cut. That's expected. And then after that, a sniff check will be done by one of the recovery folks, and that's just to ensure that there is no vapors or anything that would pose a risk to the recovery personnel or the crew themselves as they egress the capsule. And so at this point, the heat shield is now pointed towards the Earth and is really getting ready to do the heavy lifting of protecting the capsule. And of course, more importantly, the crew inside from the over 3,500 degree Fahrenheit that's going to be exposed to as the Dragon capsule enters the Earth as part of their recovery operations. Continuing to hear good call-outs that the deorbit burn is going as expected. Dragon systems are looking good. And of course, the crew is monitoring every step of the way, checking in.
Freedom, SpaceX. Deorbit burn complete. Performance nominal. Nose cone closure is initiated.
Freedom copies, nominal, deorbit burn. Glad to hear it. And nose cone closure initiated.
News nominal deorbit burn, and also heard the call out that the nose cone procedure is going to begin.
So in the background, Dragon is currently inhibiting those forward bulkhead Draco thrusters that we just used to complete the deorbit burn, ensuring it's safe to latch the nose cone shut for re-entry. Also, the vehicle has initiated the nitrox suit purge. This will help keep Chell, Bob, Jessica, and Samantha cool and comfortable during re-entry. At this point, that nose cone is closing and protecting the forward hatch for re-entry. Chell, Bob, Jessica, and Samantha are using their screens, as we mentioned, to monitor the locking of the nose cone, which is done by a set of hooks. As they enter through the atmosphere, it's really going to slow them down. Right now, they're going a little more than 17,000 miles per hour, but as they re-enter the Earth's atmosphere, once they come out on the other side, they'll be going much slower, and then the parachutes will just continue to slow them down from 350 miles per hour to a little less than 20 at the time that they splash down.
And also during re-entry, there will be a period where that heat builds up around the capsule. There'll be plasma that builds up around the capsule. So there will be a blackout zone, which is normal. It lasts about 6 minutes long. And then once we get through that blackout zone, then we'll confirm confirmation with the crew to make sure that they still can communicate with the ground here in mission control. The nose cone sequence is complete, meaning that the nose cone is now officially closed. As we begin the second half of entry, Dragon is now beginning to inject cooled nitrox into the air being delivered to the suits worn by Chell, Bob, Jessica, and Samantha. Now again, this is what will allow the crew to remain comfortable while external temperatures reach 3,500 degrees Fahrenheit. Now the heat shield is pointing forward, leading the capsule to the landing site. And speaking of the heat shield, Dragon's primary heat shield is comprised of Pica 3.0, which stands for Phenolic Impregnated Carbon Ablator. First generation Pica was first developed by NASA for studying and sampling comets within our solar system.
And SpaceX partnered with NASA to develop Pica X, which was the second generation product used on all Dragon 1 CRS missions that successfully resupplied the space station on 20 missions. Then Pica 3.0 was developed specifically for use on Dragon 2 crew and cargo with enhanced structural and thermal properties that optimize the heat shield and drove down costs and mass.
Now, the remainder of the Dragon capsule is comprised primarily of a SpaceX proprietary ablative material. It's another class of thermal protection which is lighter weight versus Pica and protects the underlying composite material or structure during re-entry to ensure the structural capabilities are maintained. Now, after Crew Dragon Freedom has re-entered the Earth's atmosphere, a series of parachutes will deploy, and that'll slow the crew's descent. Now, first will be the 2 drogue chutes, followed by the 4 main chutes to guide Dragon to its first contact with Earth since launching in April earlier this year. Dragon will automatically deploy these parachutes when different pressure and positioning sensors on the capsule detect that they are at the right speed and altitude.
Vehicle velocity at drogue deploy is approximately 350 miles per hour, and those drogue parachutes do deploy at about 18,000 feet above the water. Now, vehicle velocity at main deploy is approximately 119 miles per hour and deploy at about 6,500 feet. Vehicle velocity at water splashdown is approximately 16 miles per hour, and the highest G-load the crew will experience during re-entry is approximately 3 to 5 Gs. And so at this time, all of the recovery teams are in place. Those fast boats that we were talking about earlier have deployed.
Freedom, SpaceX for entry briefing.
And Freedom, stand by.
UHL, I have no deltas from the previously briefed tablet timeline. Dragon systems are looking healthy and ready for entry, and we have no updates for splashdown. The recovery team is ready to support, and weather's looking good. How copy?
We copy all, Arthur. We're looking forward to splashdown and seeing the recovery forces.
Crew there chatting with the core here in Mission Control Hawthorne.
SpaceX copies for tablets, restraints, and visors. Please confirm that tablets are stowed with the loops as provided on the satchels.
Copy, welcome.
SpaceX copies. Thank you, Freedom. And at this time, we're just over 5 minutes from predicted comm blackout. We will see you on the other side at 2049.
Okay, cops from LOS, and we'll see you on the flip side at 2049.
And we do have the NASA plane, the WB-57, which is up in the air, and it's equipped with some imaging technology that will be able to get pretty much the first views of the Dragon capsule on its return back to Earth. And at this time, the Dragon is working through a slewing maneuver, which means that the Dragon is helping to orient itself in the proper orientation ahead of the reentry of the Earth's atmosphere. So we are hearing that the Dragon is beginning to hit the Earth's atmosphere here, really at the upper limits of the atmosphere. So that's going to help to slow the vehicle down quite a bit, but we are now seconds away from the anticipated loss of signal.
We are currently in the comms blackout period. This is nominal, lasts about 6 minutes.
Dragon, SpaceX comm check. Freedom, SpaceX comm check.
And SpaceX, Freedom has you loud and clear, coming through 30 kilometers altitude.
Copy and concur. Expect automated chute deployment.
Freedom copies. We'll be monitoring.
And HEPS is converged. Expect nominal chute deployment altitude.
Freedom copies. Looking for nominal chute deployment.
It is absolutely phenomenal to hear from the crew on the other side of that communications blackout period.
Freedom, SpaceX, brace for drogue window.
Bracing for drones.
Core here communicating with the crew, giving them a heads up that they should feel the drogue chutes deploying here shortly, followed by the main chutes just about a minute later.
Drogue chute descent rate nominal and visual on 2 healthy drogues.
Freedom copies.
Main chute descent rate nominal, visual on 4 healthy mains.
The main chutes have deployed, slowing the Dragon vehicle down significantly.
Freedom is 1,000 meters.
Copy 1,000.
Now, Dragon has saved all propulsion systems and is now terminating the nitrox suit and cabin purges and is beginning to increase.
Freedom's at 800 meters.
Copy 800.
Dragon is beginning to increase pressure in preparation for landing. The mission control team here in Hawthorne is reporting the precise landing coordinates to the recovery team.
So we did get that confirmation on the main
600 meters.
chutes.
600.
The crew is now 600 meters away from splashing down. We do expect splashdown in about 2 minutes from now.
Landing in water is simpler, therefore more reliable, and it provides more margin against unlikely parachute.
Freedom 400 meters.
Copy 4.
Provides more margin against unlikely parachute issues. We had to learn how to make Dragon waterproof, but once you do, it is a rinse, review, and reuse type of process. And we are just about a minute away from splashdown of the Dragon vehicle back onto planet Earth, and hearing good callouts of the altitude of Dragon.
Freedom's at 200 meters. We're bracing for splashdown.
Copy, brace for splashdown.
Crew Dragon Freedom with 4 astronauts on board prepares to splash down after spending 170 days in space after launching on April 27th.
Copy, Freedom, SpaceX do splashdown and mains cut.
Welcome
Copy. Mains are
home.
cut.
Welcome home, Crew 4. Dragon Freedom has returned home, and NASA astronauts Chell, Bob, Jessica, and ES.
SpaceX Freedom. We are water uprighting and stable 1.
Copy, Freedom. We see stable 1. You are go for 4.800. And on behalf of SpaceX, welcome home. Thanks for flying SpaceX.
China has successfully launched 3 more spy satellites, as well as 2 experimental spacecraft and an alleged environmental satellite. The trio of Yogang 36 spy satellites were launched aboard a Long March 2D rocket from the Xichang Satellite Launch Center in southern China. Beijing claims the spacecraft will be used to gather scientific data, helping researchers conduct land surveys and monitoring agricultural production. However, military analysts insist they're nothing less than spy satellites, equipped with high-resolution optical and multispectral synthetic aperture radar imagery systems and electronic signals intelligence gathering surveillance technology, all designed to provide continuous reconnaissance, monitoring areas of interest to Beijing as part of what Chinese President Xi Jinping and his communist government describe as preparations for war. A day earlier, Beijing launched another Earth observation satellite, this one described as an environmental spacecraft designed to support disaster prevention, environmental protection, the monitoring of natural resources including water conservancy, agriculture, forestry and earthquakes. The SRO-1, which is equipped with a 5-meter resolution S-band radar, was launched aboard a Long March 2C rocket from the Taiyuan Satellite Launch Center in northern Jiangxi province. Earlier, 2 test satellites were launched aboard a Long March 11 rocket from a platform in the Yellow Sea. The launch took place aboard a converted barge stationed 3 kilometers offshore. The mission was China's 4th sea launch since the first back in June 2019, all using Long March 11 rockets. China now has an estimated 552 satellites orbiting the Earth, including over 228 Earth observation, surveillance or reconnaissance satellites, and that includes at least 41 Gaofeng and some 107 Yougang spy satellites. This is SpaceTime. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.